Hello, my name's Yaz, and I'm in a team with Jenny and Brianna, and today we're going to be talking about the Amazon Locker installation optimization problem. For this problem, we have 300 customers dispersed in an area that contains 30 possible lockers. For this problem, we want these 300 customers to all go to specific locations while satisfying the constraints you see on screen. So for our first constraint, we can't have customers travel more than 30 kilometers. Also, the travel distance cost per customer is $100 per kilometer. Secondly, we need all 300 customers to go to possible locker locations, while keeping in mind that every locker costs $50,000 to build.
The objective of our program is to minimize the total cost for Amazon by minimizing the total travel distance for the customers while satisfying the travel restrictions. The objective function is equal to the sum of the distance matrix times the binary variable matrix, all multiplied by $100 for all lockers 1 to 30 and customers 1 to 300, plus $50,000 for all lockers installed. This is subject to each of the constraints that were previously discussed, where L is the potential locker location, C is the customer, D is the distance matrix between every customer and potential locker location, X is the binary variable customer matrix, and Y is the variable locker array.
We wrote Cplex code to minimize the objective function. The optimal solution found is $816,400 using 8 of the 30 possible lockers. This is a demonstration of the optimal result using IBM OPL. The array of zeros and ones shows the locations of the 8 lockers being used, and the objective value is displayed above.
To begin our code, we created 3 functions that will be used to generate an array of 30 elements that represent which locker location will be chosen for installation. This array must be Boolean, meaning a 1 represents the locker that was chosen and a 0 where the locker location was not chosen. This function is calling the assign 0 function, meaning in line 32, it's generating elements which call the 0 function. In the 0 function in line 22, we are passing pointers for the array. In other words, this is going one by one in order to create an array of 30 elements. Every time an element is created, it is stored into the array. The function return array is printing the generated array, that which consists of the 30 randomly chosen binary elements. These functions are not in use until later in the program. Here, we can see the while loop that is only ran once, which ensures that we are creating only one string at a time and naming that string AR.
For this part of the code, we're creating a variable matrix that is the same size as the distance matrix that must consist of Boolean elements only, which indicates where each specific customer is going to. To start, we must discuss the constraints that were previously described. We are setting the maximum distance that the customer may travel to be 30 kilometers. We are also doing so by creating an if statement that asks if the distance that the customer is going to travel is less than 30, and which lockers are being used. Furthermore, another condition that must be met inside this if statement is if that specific locker location is being used in that iteration's array. If both conditions are met, then the program adds a 1, meaning the customer is going to that specific location, and a 0 if they are not. This is being done in a nested for loop that runs a 30 by 300 matrix, making sure that all customers are going to a locker location. This algorithm has been tested and proved to always choose the minimum or best solution. Next, we must now talk about the cost function. In the cost function, we are multiplying distance matrix by the variable matrix, which is then multiplied by 100 in order to encourage minimal distance traveled. Next, we multiply the array of which lockers were chosen in that specific iteration times the initial cost of 50,000, which is added to the cost of the distance traveled. On line 161, the variable matrix, which displays the chosen customer location and the minimum cost for that specific iteration, is printed.
On line 194, we start a loop that calls all the functions that were previously discussed. This loop runs 50 iterations. It starts by renaming the cost from the current iteration. We implemented our own simulated annealing technique and it ran correctly. However, the solution was not optimal due to the probability constraint being random. In other words, even if a solution were optimal, the program would sometimes choose a less optimal solution. To fix this issue, we began a different approach. Every time an iteration is completed, the cost is stored only if it is lower than the previous minimum cost. Here we are only printing the cost where the minimum changed because it was better than the previous minimum. Then we are printing all of the locker location arrays that were tested and also printing out the minimum cost.
We will briefly demonstrate the code running. On every iteration, an array for each of the 30 lockers is created and shows which of the 300 customers will travel to that locker. It then calculates the cost function and begins another iteration until the user-determined number of iterations has been complete. In conclusion, the Cplex code determined that the most minimal cost function was $816,000. Our most optimal solution found with the metaheuristic approach in C++ was $898,000, meaning there was only approximately a 9% error or 91% accuracy.